Hello, everyone. Welcome to pre-lecture 3. This is going to start to cover some properties of liquids now that we've gone over intermolecular forces. I also want to start by saying that all of this material that is covered in this video will not be on quiz number 1. Okay, so this is our material starting for week 2, meaning this material is fair game then for quiz 2. But again, any material in this video will not be covered in quiz number 1. Okay. All right. So we've talked about intermolecular forces and identifying them. And so the first part of this lecture, I want to talk about how those intermolecular forces can affect properties in things like liquids. And so once we've assessed kind of the intermolecular forces, we can start to understand some of these physical properties. And so the ones we're going to cover today are viscosity, surface tension, adhesive cohesive forces, and capillary action, which we will go through these in this pre-lecture video. Okay. So starting with viscosity, this is something you've probably heard of, and its technical definition is viscosity is a measure. The viscosity of a liquid is a measure of its resistance to flow. Sorry about stumbling over that phrase. Okay. So if we think of just any sort of liquid, you can think of water, gasoline, others that flow freely have a low viscosity, meaning that there's not much resistance to their flow, whereas things that are more viscous like honey or syrup or most oils will not freely flow because they have a higher viscosity. Okay. This tends to stem from molecules being more structurally complex. If we think about this simply, it usually just means that molecules are bigger. It may also mean that they have more greater strength of intermolecular forces, but many times it means they are quite large. For example, honey is essentially a polymer chain of sugar, and that is what makes it a very large molecule and also very viscous. Okay. As temperature changes, the viscosity will also change. And so basically as the molecules have more kinetic energy, when the temperature goes up, they should be able to better overcome the forces that hold them together. And then that would decrease the viscosity of our liquid. Okay, so that is viscosity. If you look at this table from your textbook, we can kind of combine what we talked about in week 1 with this. And so based on these molecular formulas given here, what intermolecular forces dominate these molecules, and you may be able to use viscosity as a hint. So if you'd like to take a moment to pause the video, look at that, you can figure that out. I'm going to go ahead and reveal the answer now. So the answer in case you were not able to come up with them. Water, its strongest intermolecular force is hydrogen bonding. Mercury is a pure element, so it only has dispersion forces. I will point out Mercury is kind of a weird one because it is only an element. It only has dispersion forces, but it has a greater viscosity than water. And that is due to its size. So Mercury is a very large atom. If you think of it, it has a much greater molecular weight than something like water. And so that's what gives it its large viscosity, is because it only has dispersion forces, but it has a very large dispersion force. Okay, so much stronger, in fact, or so much dispersion forces that it's actually stronger than the hydrogen bonding we see in water. It's also true in ethanol. So ethanol is a little bit bigger than water, meaning it's a little bit more viscous. It also has hydrogen bonding. Whereas if we compare an even bigger molecule, octane, this is gasoline, because it only has dispersion forces, it has a very low viscosity, even lower than water, right? Compare that to ethylene glycol. This is essentially antifreeze. If basically you have something you don't want to freeze, ethylene glycol is what you would add to water so that it doesn't freezes. This has molecular weight. It also has a lot of hydrogen bonding. That gives it a very high viscosity, okay? Or I guess I should say very medium. Honey and motor oil tend to be variable, but honey is something that's obviously very viscous. Again, it's a lot of sugars. that have a very large molecular weight as well as hydrogen bonding present in most of them. So it's very viscous that way, right? Next up, we have surface tension. So if you've ever seen droplets on a spider web or dew on grass, this is a common thing with water. So surface tension is defined as the energy required to increase the surface area of a liquid or by the force required to increase the length of liquid surface by a given amount. And so that's a very technical definition. We can think of surface tension as essentially cohesive forces. So cohesive meaning things want to be held together. And that's going to apply to the surface of the liquid as well. So if this is the surface of our water droplet, we know that water is pretty well stuck together because of the hydrogen bonding. And so at the surface, instead of those water molecules just falling off the droplet, they're going to want to stick to the other water molecules that are more inside the droplet. And so because, again, water has hydrogen bonding, it's a pretty sticky liquid in terms of intermolecular forces that creates a lot of surface tension, okay? So among common liquids, water exhibits a very high surface tension due to strong hydrogen bonding, like I just said. Here are some other examples here. So again, mercury, ethanol, octane. Octane is very low with only its dispersion forces, and then kind of similar as you get either a very large atom with a very large amount of dispersion forces, or if you get something with a lot of hydrogen bonding, you'll tend to see, well, I guess hydrogen bonding isn't the only key there because water obviously has a higher one, but more hydrogen bonding generally means more surface tension. Okay. And yes, it represents a relatively tough skin. I will point out this link I have posted in the notes here. If you go to that, it's a YouTube video of the surface tension of the element gallium. So gallium, like mercury, can be a liquid at close to room temperature, and it has a very, very high surface tension. I would recommend pulling up that link. Okay. Next up, we have adhesive and cohesive forces. And so this is essentially talking about the attraction of molecules to each other or to something that they are in. And so the attraction between two different molecules is adhesive. And then if we compare adhesive forces with cohesive forces, again, I kind of defined it earlier, but cohesive forces are essentially between the same molecules. And so again, adhesive are going to be interactions between different molecules. Cohesive are going to be between the same molecule. Okay. So kind of a classic example of this, where say you just got your car recently waxed, or you have a non-polar surface, then water will form droplets on that surface because the cohesive forces present in the water are going to be greater than any sort of adhesive force interacting with the surface. Okay, so that's why water will form droplets on particularly waxy things, so leaves or freshly waxed or cleaned windshields is a good example, whereas water will not tend to form droplets on things that are more polar, like, for example, a sidewalk, the surface of asphalt, something like that. Okay. Lastly, for our physical properties of liquids, we have capillary action. And so this is essentially, if you just were, to example, put a paper towel into a bowl containing wine, you can see this where the water, or in this case, the wine, moves up the paper towel through a cohesive force. And this is essentially, our paper towel is made of cellulose molecules, which come from plants. Those cellulose molecules have hydrogen bonding. You can see some OHs there. They also have some dipoles. And so the water is able to essentially latch on to those and start to move up against what it would be with gravity. Okay. So this is essentially, again, just a balance of adhesive and cohesive forces. Certain scientists calculate things like capillary action. For our purposes in Gen Chem 2, you should just essentially know what it is. Okay. All right. So this moves us into talking about phase transitions. And so we've talked about physical properties of liquids. What we're going to focus on in class this Tuesday is basically how we move between different phases of matter, particularly liquid, solid, and gas. Okay. So we can move between them in all these ways shown below. We're going to go through them one by one. In this video, I'm just going to start with our transitions between gases and liquids, since those are some of the more complex ones. Okay. And so just to start with the basic definitions, if we change from a gas to a liquid, that is called condensation, as the name for that term. And if we are doing the opposite, if we are changing from a liquid to a gas, we call that vaporization. Okay. So when the rate, essentially the speed at which condensation occurs, when that is equal to the rate of vaporization, neither of the amounts of liquid nor the amount of vapor in a sealed container will change. And so this gets us into what's called a dynamic equilibrium. Basically, in this last figure here, we have, despite maybe some sort of change in the actual molecules, the total concentration or pressure of gas remains the same. And the total amount of liquid also remains the same. Okay, we can measure that in certain apparatus that look like this, where we essentially have some sort of way to measure the pressure that's formed. Okay, and so the pressure that is exerted by that vapor is called a vapor pressure. And this is one of the measurable properties of a liquid. Okay. So things with relatively strong intermolecular forces will want to hold on to their molecules. You'll remember that when we're in a liquid, our molecules are much closer together than when they're in a gas. So things with higher intermolecular forces will recapture gas phase molecules more often when they collide with the liquid, resulting in a lower vapor pressure. And then the opposite, of course, then is true, where things with less intermolecular forces will tend to vaporize easier, and they will have then high vapor pressures. Okay. And so this can also be thought of in terms of kinetic energy. This was like our second or third slide of content this semester. So essentially, as our temperature increases, the vapor pressure of a liquid will also increase. If you just think about maybe boiling a pot of water, this would be true, where we're increasing the temperature, and so our vapor pressure above the pot of water would increase because we are increasing the amount of water that is going into the gaseous state. Okay. And just a final note that recall that at any given temperature, the molecules of a substance experience a range of kinetic energy. So it's not like they're always there. For example, at this lower temperature, the mode of our molecules, so most of them would be here at the kinetic energy. And if we raise our temperature, that will increase our mode, our highest point, but will also increase the amount that are then able to escape the liquid phase into the gas phase, with this gray line represented basically our boiling point. Okay. All right, that is it for our pre-lecture for today. Again, none of that material will be on quiz number 1, but it will be fair game for quiz number 2 in a week. Please let me know if you have any questions. Otherwise, I hope you have a great day, and I will see you in class.